Anyway, I guess I'll just get started and it'll be recording anyway. Um, cool. So this is the good do a quick recap on what we've talked about last on Monday. Cool. So, we basically just want to give it a sense about how neural network work. So these two modules, just talk about, some of the fundamentals of deep learning. And in the later part of the course, we will look into all the applications for music specifically, like in the music context. So these will be sort of like the foundation of how all these, recent deep learning models work. Um, Cool. So on Monday, we talk about this, the difference between artificial and human neuron. So, again, look at it. It's not essentially the same, but they sort of share the same idea where you basically want to aggregate information from other, neurons. So think about they are layer by layer. So every time you aggregate information from nearby neurons, you want to do some computation, you want to do some weighted sum in the artificial neuron. For human neuron, it's basically just adding up those, electro signals. Once it reached that threshold, or in the artificial neuron, we use the sigmoid function as the threshold function. Once it reached that threshold, then you shoot some signal out. So that's basically the idea of a neuron. You are doing some calculation, accumulation, aggregation, and see if it reached that threshold. And basically, you just connect a bunch of those to create an artificial neural network. And we started with like this simplest format of like fully connected V4 network. Very awkward to read its name, but anyway, you can actually turn it into a bunch of, matrix computation so that you go all the way from the input to the outputs. So basically, you can view them as a set of functions. So this is likely the most important or, most confusing part of, deep learning is that the neural network is not a single function. It's a parameterized functions. So a neural network basically represents a set of tons of functions parameterized by the parameters, weight, and biases. And our goal is basically, once you have X and you have Y, input and output, you want to compare the output with some, ground truths. That's the, essential outputs you want to model. Then you want to you know, kind of measure how close they are. And you want to use this as a, reward or, a loss or objective function to guide how you find the optimal parameters. So basically, this is the three-step for training a neural network. You build a neural network, which defines a set of functions, and then you define the objective, what is good for a function, what is bad for a function. And once you have that, you basically just want to find the optimal parameters. So today we will talk a little bit more about how you actually find the best functions. But this is like the three components of training for a neural network. We talk about regression and classification, but mostly it's just definition. Regression is anything that output a number. Classification is anything that outputs a discrete label. We talk about activation function, but I guess more importantly, this is the way how we can expand a neural network into, an X to Y mapping. So Y equal to blah, 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 X. So it's technically a function of X. So, neural network basically just represent a mapping between the input and output. That's it. And we talk about this ReLU thing. ReLU is another activation function people like to use. So you can sort of like capture a little bit about why using these activation function. So the idea is that basically we are doing sort of like inverse Fourier transform. We are sort of like synthesizing the original function through combining a bunch of ReLUs. So in this case, you just combine different ReLUs and think about how neural network is working is just to adjust the offsets of each single ReLU, but also the slope of those. So these are weights and biases that you want to optimize for so that the piecewise linear function will match better on that curve you want to model. We talk about this universal approximation theorem. It's counterintuitive, but basically that sort of shows you that, deep learning is not a must, but rather it's a more efficient way, more data efficient, more computation efficient way um, to model a function. But technically, if you have big enough, wide enough neural network, you can approximate anything you like given enough neurons. So it's very counterintuitive, but the reason why people go deeper is because they have more structures. It's just like our human brain. If we just use like a artificial neural network, like layer by layer, maybe our brain has to be, thousands times larger to do the same thing our brain is doing. But there are structure, there are loops, there are hierarchy, so that it's much more efficient. Cool. So these are some of the models back in 2015. Nowadays, it's much, much bigger. But basically, this is sort of the idea. Cool. So today we will talk about, more on deep learning. And then next we will jump into some of the application. Cool. Let me grab the slides. Cool. Yeah, as we talk about, training the neural network, basically three steps. First, you build a neural network, which defines a set of functions. So again, a neural network is a big set of functions, parameterized by weights and biases. And your goal is to sort of first define the objective, what is good for the function, and then you want to find the, optimal parameters. So you want to find the best weights and biases, which leads to the best function defined by the objective. So this sort of like, corresponds to the previously definition we talk about for machine learning, where you want to, define a task. So that's the neural network, because neural network is a mapping between input and output. So that's the task you are thinking about. And you want to define the objective, define, the performance P, and then you find the optimal parameters where you want to improve over your performance P through experience. So these finding the optimal parameters is usually done through looking into the data. Cool. So we would just go step by step. We sort of talk a little bit about building a neural network. That's the easiest format, but later we will talk about some other kinds of neural network like convolutional neural network, recurrent neural network, LSTM, transformers. But that's in the later class. But for now, assuming that we have some neural network in whatever shape, we would talk about how you define the objective and then find the optimal parameters. That's what we want to cover today. Cool. So this is again the sort of the idea of training a neural network. You have a sort of like a black box thing that you don't really care much about what's going on inside. You just know that, well, we want a neural network, and with the perfect weights and bias that would do this mapping correctly. So x and y, x to y, there's some mapping. So these f theta x will be the mapping. That's the neural network with a certain weights and bias. And then we talk about, technically you want to define good or bad between the estimated outputs, y hat, and the actual y outputs. So this is, by definition, that's the loss function we were talking about. So loss function, or sometimes called objective function, is defining how good your output is. And then you would use this loss function to guide the way how you find the optimal parameters and weights. I mean, weights and biases. So basically, loss function just measure how well the model perform. Technically in the opposite way, because that's objective function. So loss function is how bad the model perform. So the choice of loss function will depends a lot on the task and the goals. Um, so this is usually the form. So L theta. So now, one thing interesting about loss function is that loss function is a function on top of the parameters, not the x. So now you are trying to adjust the parameters so that you find the best function. So each single, combination of weights and bias will lead to a specific loss where you measure how good or bad this function is doing on this mapping. So you are technically, optimizing over the different weights and biases, and you want to find the best of that. Um, so loss function has many names, sometimes called cost function, error function, um, and the opposite. Loss function is like the bigger, the worse, the lower, the better. But sometimes people call it the opposite way. Objective function, reward function in reinforcement learning, fitness function in evolutionary algorithm and genetic algorithms. So this is like before neural network. It's still being used. So one of the fun fact of that is that the Shinkansen in Japan, the shape of that train, that's a long shape, is actually being computed or optimized by a genetic algorithm. And economists, they use, utility and profit function. But all of these sort of like define the same idea that you want to define how good a function is. So here's an example to give you the sense what objective loss function would be like. So think about a neural audio codec. So codec is basically, MP3, what else? M4A, AAC. So think about it's just a compression algorithm. So what would be a good objective to train a neural audio codec? What do we care about for codec? Any thoughts?
Probably like the final audio
Size? Size? Cool. What else?
maybe like the quality of captured impression.
How do you define that?
Yeah, that's the question. Some way to like measure audio distortion.
Yeah. So yeah, basically that's the idea. You don't necessarily know how good the output is, but you have the input, right? So that's usually how we call like reconstruction. You know, loss. So you have something and then you compress it, you decompress it, and you hope they are not so far away. So distortion, reconstruction error, but things like that. But something else? Yeah, there's another thing that people usually kind of forget. It's about the speed. So audio codec, there's so many different audio codec. Why we are still looking into different codec? Can we just stop at MP3? So one big thing is about the speed. So think about, even on your Bluetooth, you want to do, very low latency so that, you can use, your earbuds without all the latency. So earbuds actually also have like audio codec built in. So, there's a tons of things we care about for codec, mostly, reconstruction quality. At least this codec should be compressing your signal without a lot of distortion. And at the same time, bit rate, basically compression rate, you want it to be small. Otherwise, why do you want to use a codec and waste your time compressing and decompressing? And also encoding decoding speed depends on the use case. Sometimes, if you are building earbuds, then you care about the encoding and decoding speed. If you are trying to get the best, compression, results like MP4 so that you will later upload to YouTube, then pretty much you will like well, if the size is the big thing and I don't really care about this one time speed thing, then you essentially don't care about speed and more on the compression rate. So I guess the idea here is to let objective could be so many different way, and all the time you are thinking about how you can best capture what you care about. So unfortunately, as you will see later, there's just only one thing that we can trend here. So reconstruction quality is trainable because think about reconstruction quality is just it's just like doing a regression thing. Basically, you want to change those numbers so that the reconstruction will be better, capture the original sounds. For bitrate, they are likely not trainable. There's some way you can train them, but usually these are, discrete thing that you cannot train for. So, that sort of like showcase the limitation of deep learning, but at the same time, that's why, whenever you see the objective function, it's usually just a surrogate of what you're interested in rather than, something directly measuring the performance that you care about. So how do we measure reconstruction quality? Could be so many different choice. So you can measure the difference in raw waveforms. That will become some issue because, think about a waveform. If you flip it the upside down, it actually sounds exactly the same. So, 1 to 0, 0 to 1. As we talk about in Fourier transform, this doesn't change any frequency component. It's just like a phase issue that you won't hear any difference. So difference in real waveforms likely very challenging to train. But there's also some model trying to do this, and let's go WaveNet. And people thought it was impossible, but somehow, these deep neural network is crazy good just doing that. Difference in spectrograms now make more sense, but there could be divisional limitation because the phase is gone. Perceptual quality, psychoacoustics, then how do you define how you do that? So, whenever you are thinking about how you define an objective function, that's all the things that we think about. But anyway, typically what you will see as a loss function is in a very simple form. Here just a way to think through about before you even pick a loss function. So some of the common loss function would be very, very straightforward, as you might not imagine, or you might imagine. So think about, this is like a very simple neural network where you have some X and you go through one layer of neurons and you get a Y. So just one single number output. So you have another, your ground truth to think about, you are doing age or I don't know, weight estimation, and you said, 50 pounds, and then the ground truth is 60 pounds. So you want to measure how far away they are. So, this is not so hard. Basically, you just want to define a function that capture the difference between them. So, typically these are the two functions that we look into. So L1 loss, basically you just do an absolute difference between them. And for L2 loss, you do the square loss between them. And there's a lot of discussion, what's the difference between them? But technically, they have the same, if you do it perfectly, they will reach the same point. But they have sort of like different training behavior. Cool. And I usually just look at this function. This is the way how it's defined. So mean absolute error is usually just, when you sum up all the things for all the samples that you have and mean square error. So that corresponds to these two different losses. So one iconic difference between them is that L2 loss is more sensitive to outliers. So this is very tricky to see here. I usually just think about, there's a raindrop coming down. So, L1 loss will be, a raindrop coming down and it will just slowly flow through the zero. So that will be hopefully, when you train the model, it will just slowly go to that place. But now think about L2 loss. Now you have a raindrop coming down. Then it will, at the beginning, there will be a very, steep slope. So it will be very sensitive to outliers. If something is here, then it will be very steep and it will quickly go through somewhere near zero. So that's what we meant by, more sensitive to outliers, because all the outliers will be punished with a very strong, steep slope that encourage it to reach zero as soon as possible. So that's the difference between L1 and L2 loss. But technically, either works. For classification is a little bit more trickier. Yeah. So there's a bunch of math here. So what we would talk about is sort of like a simplified way of looking into stuff. But basically, for binary classification, usually we are thinking about this thing called logistic regression. So the way you can think about it is that, we want to do binary classification, then it's sort of like, is cat or not cat? So this is like 1, 0. Thing. So now you look at this sigmoid function. If you add the sigmoid function at the output for this thing, technically you can turn them into 0 and 1 decision. So everything lower than 0 will be something close to 0, and anything beyond 0 will be something between 0.5 to 1. So you can actually use this sigmoid function and use the threshold at 0.5 to do binary classification. Um, so that's basically how we can do logistic regression for binary classification. And these are all sort of, you know, um, definition of like log loss. There are some mathematics going on behind this, why we are using this. But again, look at this figure, the raindrop thing again. So this thing basically showed that if y equal 1, and if you get a raindrop, it would just drop down and go through all the way until you reach the minimum point. So it will force if your ground truth is 1, if it's cat, then you want to force everything to become a cat. And if y equals 0, then it will try to drive everything toward a 0 output. So basically, that's the idea. And it takes this shape that has some mathematics behind it. Cool. Sometimes it look like this. They are technically the same. It's very confusing at the first time you look at this. It's like, why this loss function looks so ugly. But these two are essentially the same. If you plug in y equal 1, this term got canceled out, will be 0. If you plug in y equals 0, this term got canceled out. So these two are essentially the same. It's just a very fancy way, like a shorthand. You only write one line rather than two lines. Cool. Anyway, I guess more interesting, a multi-class classification. This is the one that we will play with in the next PA, where we want to do instrument classification. So we will look into a bunch of spectrograms, and our goal is to classify the instrument of that particular spectrogram. So sort of similar to what you did in PA, not one of the PA. Look at the spectrogram, and you can pretty much guess what that spectrogram is, because just by staring at it. So that's the idea for the next VA. We want to train a neural network to do it. So basically what we want to do is this thing called multi-class classification. So you are classifying something like a spectrogram into multiple different possible instruments. So the idea here is that we have to do something else than just compiling these numbers. So what we were doing is that we will add an additional layer. It's something called softmax. So the idea here is that essentially what we want to do is that the actual output y here is something, either 0 or 1. It will be a 1 for the correct output and 0 for everything else. So everything will sum up to 1. So you can think about it like a probability-ish thing where it's 100%, a trumpet sound, but 0% on all the other possible sound like guitar, piano, bass, drums, whatever. So it will sort of like, something like a probability that sums to 1, and you have 100% chance on the correct, outputs. So that's essentially what we want to do. We want to turn a bunch of real numbers into something that sums to 1, where you have a much larger probability to be at the correct outputs and lower probability for all the incorrect outputs. So that's essentially what we want to do, real value numbers to probability-like numbers. And that's what we call softmax. This is the, again, mathematics. So, you basically take exponential and then sum them up and do the, normalization. Um, so that's it. So stare at it, look very um, ugly. But all you need to um, know is that the intuition just to map a bunch of numbers so that you can keep their relative magnitudes. So this is like an example, I believe. So softmax, what we are trying to do is that a bunch of real numbers, we want to map them into something that sum to one and keep their relative magnitude. So what's going on within softmax can be, summarized like this. So basically you take exponential of all the numbers and then you just do normalize. So you sum them up and divide it by all by their sum, basically. So we will have an example later. So this is basically just softmax. So do exponential and then do normalization so that everything sums to one. So think about this particular example. You have like 73.5, 2.6, negative 12.8. So now you can do, exponential and then you divide it by the sum. So you will get something like 0.98, 0.02, 0.00. So now you see that it actually softmax because of the exponential. It will force everything to be very extreme. So in this case, the larger the input, the higher, probability or technical not probability, but think about it something like probability, the higher chance that you will, higher weight that you allocate to that particular output. So, now think about what will be this model is doing. So now you compare with the ground truth, say this is the correct label, like the trumpet, and, so this will be one, for the ground truths and 0, 0, 0 for the other things. So over the time, what you are trying to train this model for is technically just increasing the probability of the correct label and, lower the probability for other label. Questions? Good. Um, Yeah, I guess softmax is a thing that the first time I look at it was like, oh, cool. And then later on, you were like, why? And then at some point, you will be like, okay, fine. I would just keep it that way. There's a lot of like mathematics going on under the reason why we have exponential. But for most of the case, when you are using it rather than trying to understand the math, then the idea is to turn, the intuition is to turn a bunch of real numbers into something that sum to one while keeping their relative magnitude. Cool. And technically, softmax is like the multivariate version of sigmoid. Cool. So these are the loss function. I guess I've just put here. You likely won't remember it and you don't need to remember them, but just to let you know, there's so many different format. And whenever you see something like this, it's actually the things that we would talk about. So, binary class entropy, some usually look like this when you read a paper, look ugly, but that's binary class of cross entropy. For cross entropy, usually it doesn't look like that. They are technical, these two are technically the same if you stare at it for a longer time. But basically, usually you will see something like this, yi log yi negative, and the sum. So binary class entropy, if you stare it long enough, so y will be either 1 or 0. So, these two terms, only one of them will be 1. Everything else will be 0. And that's the same for, cross entropy, because y1 to yi, there's will be 1, 1. Everything else will be 0. So again, only one of them will be 1. So they are technically the same, just that it's one for, two binary things, one for, multi-class classification. And this thing we usually call it log likelihood. But anyway, those a lot of term. And, whenever you read a paper, you will get confused at some point. It's like cross entropy, log likelihood. I don't know. things like that. It just keep popping up. And negative log likelihood, NLL, CES, CEE, like cross entropy, CEL, cross entropy loss, things like that. Cool. But anyway, these are just some math. And technically, in PyTorch, you would just call something like PyTorch the loss and cross entropy, and then put your stuff into it, and it will calculate for you. Cool. So next we will talk about optimization. Again, likely when you are working with PyTorch, everything will be automatic, but just to give you the sense, what's going on under the hood, so that when you are working with these, models, you sort of feel a little bit more grounded rather than, everything is like imaginary. Cool. So again, build a neural network, which defines a set of functions. So this is like the way how we look at it. Now you have a function, f, which maps from x to y. That's parameterized by the theta, like the parameters. So now you want to define the objective. So this basically, it's a loss function defined on top of theta. So theta is the thing that we want to optimize, not x or y. We want to optimize the weights and biases. And you want to find optimal parameters, which leads to the best function. So technically, what we are trying to do is this optimization. We want to minimize the loss function of theta, and argmin, meaning that we are interested about the parameters that leads to the minimum loss function, not the loss function itself. So argmin basically means that you are looking for the theta that leads to the minimum theta, and that will be your ideal, the optimal parameters. So, technically, this is the optimization problem that we are trying to solve. Cool. So in the next few slides, we'll talk about how we can do this. So there are actually many, many, many ways to optimize the parameters of a neural network. So, gradient descent, and all the thing we would talk about, like nowadays, people are mostly using gradient descent, but that's just one way of optimizing the parameters. That's important because people always thought, gradient descent is the only way, but that's not true. It's just that nowadays it's much more efficient because of GPU. But also there is a tons of, optimization challenge, and somehow gradient descent work pretty well if given enough, computation budget. You can also use search or genetic algorithms. So there's some papers later on we will see that actually didn't use any gradient descent, and you can do something very interesting. Cool. So gradient descent. It's just an algorithm so that you can, algorithmatically to find the perfect, optimal parameters. So in the next few slides, I will just show you through this sort of like example and some animation to show you that, how can we use gradient, or gradient is basically a fancy word for slope when you have, in a higher dimension space. So gradient, think about it, slope. Basically, how can you use slope to suggest a good direction to tune the parameters? So think about this shape. This is the objective function. So the loss function. So your goal is to find the lowest point. So, think about, the raindrop thing. So you put the raindrop, and then you would just naturally flow through and find the optimal point. But that's not, how algorithm work. There's no way your model will just follow that things and go through that. But you somehow get the idea that, well, the slope, the gravity, sort of like hint you about there's some way that you can do the optimization. And gradient descent is just a way to capture that and turn it into an algorithm that you can actually optimize or compute for. So gradient, again, is derivative or slope for a vector, matrix, or tensor. So it's just a fancy word for think about it just like slope. So this is a pseudocode of this gradient descent algorithm. Stare at it, it sounds very like alien language, but this is basically it, 2 lines. pick an initial weight vector, W0, to start with, and the learning rate, eta, I think that's called eta. Repeat until convergence, WT plus 1 equal WT minus eta gradient FWT. That's it. This is like elegant gradient descent. So let's look into how it works actually. So you have a W0. This is it. So this is the gradient with respect to weight W. So, as I said, this thing is basically the slope. When you think about, gradient, it's more like a slope in a higher dimension. But now we are thinking about this 1D thing, then basically just slope. So if you look at this slope is actually positive. So it's actually going up on the right-hand side. So you can pretty much guess that, this slope, we want to go against the direction of the slope. And that's essentially why there's a negative sign there. So now what you want to do is to do the adjustment. The adjustment will be negative, the learning rate times the slope. So it will be something smaller than 0. That's why you are going toward the opposite direction. So the core idea of gradient descent is that once you know the slope, you want to do the opposite way, but tune it down by learning rate. So that's essentially what you were trying to do. Now you update W0 equal W1 because W1 is essentially just W0 minus the thing. So it will be smaller than that. Now repeat until convergence. So you do the same thing. So now you are at this point. Now you compute the slope at that point. Now the slope becomes smaller. So you want to do the adjustment again. Now, because the slope is smaller, your learning rate is the same. So this thing, the adjustment becomes smaller. So it will move it still to the left, but now with a smaller, adjustment. And so you just keep doing this. Now you move to W2, you have the slope even smaller, and you make an even smaller adjustment. And hopefully, over the time, the slope keep dropping, the gradient becomes smaller, but at the same time, your adjustment becomes smaller. And, you can see that at the end, the convergence will reach that optimal point. Questions on this? So that's basically gradient descent, a visualize of what's going on. Oh, good.
So
Yeah.
you can only really do that if your loss function is a function.
Yeah.
You mentioned earlier there's like some loss functions that like you would search over instead of like training.
So gradient descent, first you have to compute the gradient. So if it's not continuous, there's no way you can compute the gradient. So think about, things that just doesn't, so think about there is like a shot window, then there's no way you can define a gradient here. Technically for gradient descent, if it's continuous, you can still use gradient descent. You don't really need to have gradient at each single point. So think about like the L1 loss. That's one of the iconic case where it's not differentiable at the bottom part, like the V-shaped thing. But you don't really care because you won't reach that point. Technically, if you reach that point, you are done. So technically, you won't reach that point, but all the way everywhere you have gradients. So the idea of gradient descent is that hopefully during your optimization process, you get gradients all the time. And whenever it's not defined, you need to figure out a way. If you can figure out a way to still provide some gradient to it, then you can still optimize it. The other challenge would be, something that's just totally indifferentiable. Think about, sampling rate, bit rate, compression rate. Those things are just like 1, 2, 3. There's just no way you can optimize over it. So that's the thing why we call something that's just not differentiable, that you cannot do gradient descent. And yeah, we won't cover it today, but think about, this thing become like too dip, then gradient descent might not work because it will just drop to the first dip and then it won't go to the next dip. So imagine that you have 2 dip and one dip is like lower than the other. You essentially want to reach this. So gradient descent will only find you the local minima. I actually have a video for that, I guess. Not video. So that's essentially some of the challenge. Gradient descent will work perfectly when there is just one single global minimum. I mean, the local minimum is the global minimum. Then you can use gradient descent to, find it. And everything we talk about, or the optimizer, there are so many different optimizer we talk about in deep learning, are essentially, addressing the issue where now potentially you have so many different local minimum. How can you find the best one? Yeah. I guess this is a better visualization. So this is like a 3D case. So for neural network, it will be more than 3D. It will be million dimension. But the same idea. Now you have a raindrop, you drop it. So gradient descent is that the raindrop. How you determine how it goes? It's basically measuring the slope, right? So technically, that's just sort of like similar to gradient descent. So, if you drop a raindrop here, it would just flow, 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 flow all the way to the local minima here, there. And if you drop it somewhere else, so this is the initialization. So if you initialize it somewhere here, then it will drop all the way to the lowest part, the sea level. And for this case, it will also turn and, all the way flow into the sea level. So now you also see what's the problem of gradient descent. For this case, if you initialize it badly, it will stop here and won't reach the minimum value. In this case, the minimum value will be the sea level, right? So it depends a lot on the initialization. And so back in the days, nowadays, people are still looking into how to do a good initialization and good optimization. But nowadays we have very powerful initialization strategy, normalization strategy, but also optimization strategy so that you can actually try to escape. So there's a lot of way we won't talk about today, but after we talk a little bit more about some of the downstream tasks, we will come back and talk about those. So you can imagine one thing we can do is like momentum. So momentum meaning that well now you get a raindrop and it goes through here, but think about if it's a ball, it won't just stop there. It could just keep going. That's the momentum. So, if you have a momentum, then potentially you drop a ball here, it would just go up and then just reach this point and then flow out. So that's one of the idea. There are so many different ideas, and you can even just randomly shake it, so that introduce some stochastic randomness, so that stuff here will be shaken and potentially drop out of the track, basically. But anyway, here we're still imagine that in the perfect, utopia where you don't have those issues. Now, hopefully gradient descent can solve a lot of things already. So the last thing I think there's a lot more. But anyway, this is one of the things that's very, very challenging to explain. So backpropagation is likely, a lot of people say this will be the next sort of like FFT, you will like a very important algorithm. But backpropagation basically just an efficient way to compute the gradients. And there's no easy way. We can sort of like explain how it works. But the idea is that we want to compute the gradients, but it's so hard to compute the gradients. So I would just show you this very nice video. I think it explains much better than I could. Let me show you here.
Because the cost function involves averaging a certain cost per example over all the tens of thousands of training examples, the way that we adjust the weights and biases for a single gradient descent step also depends on every single example. Or rather, in principle it should, but for computational efficiency, we're going to do a little trick later to keep you from needing to hit every single example for every single step. In either case, right now, all we're going to do is focus our attention on one single example, this image of a 2. What effect should this one training example have on how the weights and biases get adjusted? Let's say we're at a point where the network is not well trained yet, so the activations in the output are going to look pretty random, maybe something like 0.5, 0.8, 0.2, on and on. Now we can't directly change those activations, we only have influence on the weights and biases, but it is helpful to keep track of which adjustments we wish should take place to that output layer. And since we want it to classify the image as a 2, we want that third value to get nudged up, while all of the others get nudged down. Moreover, the sizes of these nudges should be proportional to how far away each current value is from its target value. For example, the increase to that number 2 neuron's activation is in a sense more important than the decrease to the number 8 neuron, which is already pretty close to where it should be. So zooming in further, let's focus just on this one neuron, the one whose activation we wish to increase. Remember, that activation is defined as a certain weighted sum of all of the activations in the previous layer, plus a bias, which is all then plugged into something like the sigmoid squishification function, or a ReLU. So there are 3 different avenues that can team up together to help increase that activation. You can increase the bias, you can increase the weights, and you can change the activations from the previous layer. Focusing just on how the weights should be adjusted, notice how the weights actually have differing levels of influence. The connections with the brightest neurons from the preceding layer have the biggest effect, since those weights are multiplied by larger activation values. So if you were to increase one of those weights, it actually has a stronger influence on the ultimate cost function than increasing the weights of connections with dimmer neurons, at least as far as this one training example is concerned. Remember, when we talk about gradient descent, we don't just care about whether each component should get nudged up or down, we care about which ones give you the most bang for your buck. This, by the way, is at least somewhat reminiscent of a theory in neuroscience for how biological networks of neurons learn, Hebbian theory, often summed up in the phrase, neurons that fire together wire together. Here, the biggest increases to weights, the biggest strengthening of connections, happens between neurons which are the most active and the ones which we wish to become more active. In a sense, the neurons that are firing while seeing a 2 get more strongly linked to those firing when thinking about a 2. To be clear, I really am not in a position to make statements one way or another about whether artificial networks of neurons behave anything like biological brains, and this fires together wire together idea comes with a couple meaningful asterisks. But, taken as a very loose analogy, I do find it interesting to note. Anyway, the third way that we can help increase this neuron's activation is by changing all the activations in the previous layer. Namely, if everything connected to that digit 2 neuron with a positive weight got brighter, and if everything connected with a negative weight got dimmer, then that digit 2 neuron would become more active. And similar to the weight changes, you're going to get the most bang for your buck by seeking changes that are proportional to the size of the corresponding weights. Now, of course, we cannot directly influence those activations. We only have control over the weights and biases. But just as with the last layer, it's helpful to just keep a note of what those desired changes are. But keep in mind, zooming out.
Wait a second. Point to pause, I guess. So the idea is that backpropagation is keeping track of what you intentionally want it to be, and then you try to do it again and again to propagate back to the initial.
Out one step here. This is only what that digit 2 output neuron wants. Remember, we also want all of the other neurons in the last layer to become less active. And each of those other output neurons has its own thoughts about what should happen to that second to last layer. So, the desire of this digit 2 neuron is added together with the desires of all the other output neurons for what should happen to this second to last layer. Again, in proportion to the corresponding weights, and in proportion to how much each of those neurons needs to change. This right here is where the idea of propagating backwards comes in. By adding together all these desired effects, you basically get a list of nudges that you want to happen to the second to last layer. And once you have those, you can recursively apply the same process to the relevant weights and biases that determine those values, repeating the same process I just walked through and moving backwards through the network. And zooming out a bit further, remember that this is all just how a single training example wishes to nudge each one of those weights and biases. If we only listened to what that 2 wanted, the network would ultimately be incentivized just to classify all images as a 2. So what you do is you go through this same backprop routine for every other training example, recording how each of them would like to change the weights and the biases. And you average together those desired changes. This collection here of the averaged nudges to each weight and bias is, loosely speaking, the negative gradient of the cost function referenced in the last video, or at least something proportional to it.
Cool. So I guess that's basically SWAM, the idea of backpropagation. So you want to look at the, the final value. You want to see how you sort of like tune each of numbers. You want to know where you want to increase or decrease it, to what extent. And then you keep doing that back to the first layer. So that's how we call that. It's a backpropagation. So you want to sort of like reverse that, process about how you change each of the weights and bias from the last layer all the way to the first layer. So basically that's the 2 things we talk about in in deep learning. So sometimes when you're working with PyTorch, there's will be like something like loss.backward that's basically showing this. So the forward pass is the things that we care about when you are doing inference. If you are not doing training, this is what you care about. This is just compute the estimation y, the output from the x. So that's all the the math we talk about. Like it's technically just a function and a bunch of metrics up, matrix multiplication, bias, and some activation function. But it's just a bunch of computation. But the more interesting part of that is that you want to do this backward pass where you basically want to do the gradient computation, but at the same time, you want to record what's the ultimate gradient that you want and how you adjust all the weights and biases to fulfill that, change so that you lead y your, current estimation towards a better estimation. So you can do this is a gradient partial L over partial H L minus 1. So you're basically looking at the loss function and looking at the last hidden layer. How would you change the weight and bias of that layer to make it better? And then you compute the last second layer, the third layer, the second layer, the first layer. So you can all the way, do this backward pass, which we call this backward pass. But basically, this is how you compute when you do, PyTorch, when you do loss backward. Basically, you will compute the loss function layer by layer. So it's sort of like the same as forward pass, where you compute all the way toward y from x, and then do the matrix multiplication again and again until you reach y. Now you want to compute the gradient. You want to adjust all the weights and biases. But how you compute it is that you first do the first layer, the last layer, and third layer, second layer, and first layer. So it's the opposite way. And this is essentially what you would do, what PyTorch would do when you call this loss that backward. So this usually is the most computationally intense step of the whole training script, as you will see in one of the homework. Likely you will measure it, but this is essentially the core of deep learning. All the GPU thing, why we are doing all sort of these things are to, increase this, gradient computation speed so that you can train these model much more efficiently. Of course, forward pass is important at the inference times because that's the thing that you will keep using it. Backward pass is just for training. But think about the difference between training and inference. It's like training, if you want to do million times of training, then essentially it's, million times more than your inference time. So, we always need to balance that. So you want a fast forward pass, but at the same time, you also want a very fast backward pass. Any question on this? every time I look at this video, I have different thought. So, there's no way you will get the full picture in the first glance. But, the more you dig into deep learning, the more mysterious as you feel likely. Any questions on that? Oh, good.
So like the computer like does the derivatives. I've heard like automatic differentiation, where it's like doing it computationally instead of like, does it use the formula or does it?
It does use the formula. Okay. So the auto, yeah, that's a good point. So the auto differentiable thing is actually pretty interesting because basically in PyTorch is that every single function you will record its derivative. So, if it's x, then it's just, 1. If like x squared, it would be 2, 2x. So, it basically for every single function in PyTorch, you will need to define its derivative backward function. So by automatic differentiation, it's not like you are doing calculus on the fly. You actually know every single function what's its derivative. So that's what we meant by backward function. So on the forward pass, you have to compute all these weights and plus sign, right? Now in the backward pass, you actually know all these formula. You know the formula. You just want to compute the numbers. So formula is actually already stored in PyTorch. And that's why, when you define a custom function in PyTorch, you have to define a property of that function where you define the backward pass. So usually every single function in PyTorch, you will have the forward method and backward method. So forward will define how you flow through the forward pass and the backward pass. So that's the interesting part of PyTorch, how it, implemented. So again, technically, you already know the formula. You just need to compute the numbers. Yeah. So you are not doing calculus on the fly. Yeah. Cool. So I guess again, gradient descent is a way, once it's like a way to formulate the raindrop thing where, look at the curve, where exactly you are going. But, for the model, there's no way what the essential curve is like. So you only knows that at every single point, what's the slope at that point is like, and you just keep following the slope. So think about, it's dark on the mountain and you only have a headlight point down on your feet. You only know what the slope is like, so you can go and then you can step based on the slope. So the steeper it is, then you walk a bigger step because you are likely far away from the dip. But if the slope is not that steep, then you wanna proceed more cautiously. So that's the idea of gradient descent, and backpropagation is just a way. Now, you have all these gradient thing. It's very challenging to compute what's the inference of these weights and biases to the final output because they are so far away. So the gradient descent, the backpropagation thing is that, well, look at these, bias and parameter, weights and bias is like directly inferencing the output. But for the first layer, how do you do it? So that's why you want to do, backpropagation so that as in the video they showed that, well, now you know how you want to, nudge these values. And then with this, you can see how you nudge these values. And then you can see how you want to nudge these values. And then you see how you want to nudge these values so that you can determine how you change these weights and biases. And that's the backward pass. Cool. I think we are running out of time. But anyway, we will finish it next Monday on the last part of this piece, training validation task. It's just another important concept of machine learning. And then we will jump into the classification, music classification. We will start by talking about, music analysis. Classification would be the simplest. So separation, or sort of like analytic part of music, AI, and then we will jump into, the creative side of those, and then finally retrieval, recommendation, and then the processing part. Cool. So we are getting there slowly. Should be more interesting over time, hopefully. Yeah. Cool.